Hello and welcome. My name is Alan and today we'll be doing more ideas and opinions of Albert Einstein. Today we'll be reading two pieces. So let's get into this. The first piece is called Maxwell's Influence on the Evolution of the Idea of Physical Reality. On the 100th anniversary of Maxwell's birth, published 1931 in James Clerk Maxwell, a commemoration volume, Cambridge University Press. The belief in an external world independent of the perceiving subject is the basis of all natural science. Since perception only gives information of this external world or of physical reality indirectly, we can only grasp the latter by speculative means. It follows from that our notions of physical reality can never be final. We must always be ready to change these notions. That is to say, the axiomatic basis of physics, in order to do justice to perceived facts in the most perfect way logically. Actually, a glance at the development of physics shows that it has undergone far-reaching changes in the course of time. The greatest change in the axiomatic basis of physics, in other words, of our conception of the structure of reality since Newton laid the foundation of theoretical physics, was brought about by Faraday's and Maxwell's work on electromagnetic phenomena. We will try in what follows to make this clearer, keeping both earlier and later developments in sight. According to Newton's system, physical reality is characterized by the concepts of space, time, material point, and force, reciprocal action of material points. Physical events, in Newton's view, are to be regarded as the motions governed by fixed laws of material points in space. The material point is our only mode of representing reality when dealing with changes taking place in it, the solitary representative of the real, insofar as the real is capable of change. Perceptible bodies are obviously responsible for the concept of the material point. People conceived it as an analog of mobile bodies, stripping these of the characteristics of extension, form, orientation in space, and all inward qualities, leaving only inertia and translation, and aiding the concepts of force. The material bodies, which had led psychologically to our formation of the concept of the material point, had now themselves to be regarded as systems of material points. It should be noted that this theoretical system is in essence an atomistic and mechanistic one. All happenings were to be interpreted purely mechanically, that is to say, simply as motions of material points according to Newton's law of motion. The most unsatisfactory side of this system, apart from the difficulties involved in the concept of absolute space, which have been raised once more quite recently, lay in the description of light, which Newton also concerned in accordance with his system as composed of material points. Even at the time of question, what in that case becomes of the material points of which light is composed when the light is absorbed was already a burning one. Moreover, it is unsatisfactory in any case to introduce into the discussion material points of quite a different sort which had to be postulated for the purpose of representing ponderable matter and light respectively. Later on, electrical corpuscles were added to these, making a third kind, again with completely different characteristics. It was further a fundamental weakness that the forces of reciprocal action by which events are determined had to be assumed hypothetically in a perfectly arbitrary way. Yet this conception of the real accomplished much. How came it that people felt themselves impelled to forsake it? In order to put his system into the mathematical form to all, Newton had to devise the concept of differential quotients and propound the laws of motion in the form of total differential equations, perhaps the greatest advice in thought that a single individual has ever privileged to make. Partial differential equations were not necessary for this purpose, nor did Newton make any systematic use of them. But they were necessary for the formulation of the mechanics of deformable bodies. This is connected with the fact that within these problems, the questions of how bodies are supposed to be constructed out of material points has no importance to begin with. Thus, the partial differential equation moved theoretical physics as a handmaid, but has gradually become mistress. This began in the 19th century when the wave theory of light established itself under the pressure of observed fact. Light is empty space in an empty space was explained as a matter of vibrations of the either, and it seemed idle at the stage, of course, to look upon the latter as a conglomeration of material points. Here, for the first time, the partial differential equation appeared in the natural expression of the primary realities of physics. In the particular development of theoretical physics, the continuous field thus appeared side by side in the material point as the representative of physical reality. This dualism remains even today, disturbing as it must be to every orderly mind. If the idea of physical reality has ceased to be purely atomic, it still remained for the time being purely mechanistic. People still try to explain all events as the motion of inert masses. Indeed, no other way of looking at things seemed conceivable. Then came the great change, which will be associated for all time with the names Faraday, Maxwell, and Hertz. The lion's share of the revolution fell to Maxwell. He showed that the whole of what was then known about light and electromagnetic phenomena was expressed in his well-known double system of differential equations, in which The electric and the magnetic fields appear as dependent variables. Maxwell did indeed try to explain or justify these equations by the intellectual construction of a mechanical model. But he made use of several such constructions at the same time and took none of them really seriously, so that the equations alone appeared as the essential thing in the field strengths of the ultimate entities, not to be reduced to anything else. By the turn of the century, the conception of electromagnetic field as an ultimate entity had been generally accepted, and serious thinkers had abandoned the belief in the justification or the possibility of a mechanical explanation of Maxwell's equations. Before long, they were, on the contrary, actually trying to explain material points and their inertia on field theory lines with the help of Maxwell's theory, an attempt which did not, however, meet with complete success. Neglecting the important individual results which Maxwell's life work produced, and in important departments of physics, and concentrating on the changes wrought by him in our conception of the nature of physical reality, we may say this: before Maxwell, people conceived of physical reality insofar as it is supposed to represent events in nature as material points, whose changes made exclusively of motions which are subject in total differential equations. After Maxwell, they conceived physical reality as represented by continuous fields, not mechanically explicable, which are subject to partial differential equations. This change in the conception of reality is the most profound and fruitful one that has come to physics since Newton. But it has at the same time to be admitted that the program has by no means been completely carried out yet. The successful systems of physics which have been evolved since rather represent reason bear a provincial, logically complete character, although they may have achieved great advances in certain particulars. The first of these calls that calls for mention of Lorentz's theory of electrons, in which the field and the electrical corpuscles appear side by side as elements of equal value for the comprehension of reality. Next come the special and general theories of relativity, which, although based on ideas connected with the field theory, have so far been unable to avoid the independent introduction of material points and total differential equations. The last and most successful creation of theoretical physics, namely quantum mechanics, differs fundamentally from both the schemes which we shall, for the sake of brevity, call the Newtonian and the Maxwellian. For the quantities which figure in the laws make no claim to describe physical reality itself, but only the probabilities of the occurrence of a physical reality that we have in view. Dirac, to whom, in my opinion, we owe the most perfect exposition logically of this theory, rightly points out that we would probably be different, for example, to give to the theoretical description of a photon, such as would give enough information to enable one to decide whether it should pass a polarizer placed obliquely in its way or not. I am still inclined to the view that physicists will not, in the long run, content themselves with that sort of indirect description of reality, even if the theory can eventually be adapted to the postulate of general relativity in a satisfactory manner. We shall then, I feel sure, have to return to the attempt to carry out the program, which may be described properly as the Maxwellian, namely, the description of physical reality in terms of fields which satisfy partial differential equations without singularities. So yeah, Einstein talking about Maxwell's importance in the understanding of reality and what is physically real. How he advanced from what Newton had done, and how he really gave us a bit more of an understanding in the fields of electricity and magnetism, which we now know it's a natural force of the universe, the electromagnetic force. But yeah. Second piece we're going to read is called On the Method of Theoretical Physics. The Herbert Spencer Lecture, delivered at Oxford, June the 10th, 1933, published in Mein Weltbild, Amsterdam, Corrido Verlag, 1934. If you want to find out anything from the theoretical physicists about the methods they use, I advise you to stick closely to one principle. Don't listen to their words. Fix your attention on their deeds. To him who is a discoverer in this field, the products of the imagination appear so necessary and natural that he regards them and would like to have them regarded by others, not as creations of thought, but as given realities. These words sound like an invitation to you to walk out of this lecture. You will say to yourselves, the fellow's a working physicist himself, and ought therefore to leave all questions of structure of theoretical science to the epistemologists. Against such criticism, I can defend myself from the personal point of view by assuring you that it is not at my own insistence, but at the kind invitation of others that I have mounted this rostrum, which serves to commemorate a man who fought hard all his life for the unity of knowledge. Objectively, however, my enterprise can be justified on the ground that it may, after all, be of interest to know how one who has spent a lifetime in striving with all his might to clear up and rectify its fundamentals looks upon his own branch of science. The way in which he regards its past and present, and may depend too much on what he hopes for the future and aims at in the present. But that is the inevitable fate of anybody who has occupied himself intensively with a world of ideas. The same thing happens to him as to the historian, who has in the same way, even though perhaps unconsciously, groups actual events around ideas which he has formed for himself on the subject of human society. Let us now cast an eye over the development of the theoretical system, paying special attention to the relations between the content of the theory and the totality of empirical fact. We are concerned with the eternal antithesis between the two inseparable components of our knowledge, the empirical and the rational, in our department we reverence ancient Greece as the cradle of Western science. Here, for the first time, the world witnessed the miracle of a logical system which proceeded to step to step with such precision that every single one of its propositions was absolutely indubitable. I refer to Euclid's geometry. This admirable triumph of reasoning gave the human intellect the necessary confidence in itself for subsequent achievements. If Euclid failed to kindle your youthful enthusiasm, then you were not born to be a scientific thinker. But before mankind could be ripe for a science which takes in the whole of reality, a second fundamental truth was needed, which only became common property among philosophers with the advent of Kepler and Galileo. Pure logical thinking cannot yield us any knowledge of the empirical world. All knowledge of reality starts from experience and ends in it. Propositions arrived at by purely logical means are completely empty as regards reality. Because Galileo saw this, and particularly because he drummed it into the scientific world, he is the father of modern physics. Indeed, of modern science altogether. If, then, experience is the alpha and the omega of all our knowledge of reality, what is the function of pure reason in science? A complete system of theoretical physics is made up of concepts, fundamental laws which are supposed to be valid for these concepts and conclusions to be reached by logical deduction. It is these conclusions which must correspond with our separate experiences in any theoretical treatise. Their logical deduction occupies almost the whole book. This is exactly what happens in Euclid's geometry, except that there are fundamental laws. The fundamental laws are called axioms, and there is no question of the conclusions having to correspond to any sort of experience. If, however, one regards Euclidean geometry as the science of the possible mutual relations of practically rigid bodies in space, that is to say, treats it as a physical science without abstracting from its original empirical content, the logical homogeneity of geometry and theoretical physics becomes complete. We have thus assigned to pure reason and experience their places in a theoretical system of physics. The structure of the system of the work of reason, the empirical contents of their mutual relations, must find their representation in the conclusions of the theory. In the possibility of such a representation lie the sole value and justification of the whole system, and especially of the concepts and fundamental principles which underlie it. Apart from that, these latter are free inventions of the human intellect, which cannot be justified either by the nature of that intellect or in any other fashion a priori. These fundamental concepts and postulates, which cannot be further reduced logically, form the essential part of a theory which reason cannot touch. It is the grand object of all theory to make these irreducible elements as similar as and as few in number as possible without having to renounce the adequate representation of any empirical content whatever. The view I have just outlined of purely fictitious character of the fundamentals of scientific theory have by no means the prevailing one in the 18th and 19th centuries. But it is steadily gaining ground from the fact that the distance in thought between fundamental concepts and laws on one side and on the other the conclusions which have to be brought into relation with our experience grows larger and larger, the simpler the logic structure becomes. That is to say, the smaller the number of logically independent conceptual elements which are found necessary to support the structure. Newton, the first creator of a comprehensive workable system of theoretical physics, still believed that the basic concepts and laws of his system could be derived from experience. This is no doubt the meaning of his saying, hypotheses non fingo. Actually, the concepts of time and space appeared at that time to present no difficulties. The concepts of mass, inertia, and force, and the laws connecting them, seemed to be drawn directly from experience. Once this basis is accepted, the experience, and it was reasonable. Once this basis is accepted, the expression for the force of gravitation appears derivable from experience, and it was reasonable to expect the same in regard to other forces. We can indeed see from Newton's formulation of it that the concept of absolute space, which comprised that of absolute rest, made him feel uncomfortable. He realized that there seemed to be nothing in experience corresponding to this last concept. He was also not quite comfortable about the introduction of forces operating at a distance. But the tremendous practical success of his doctrines may well have prevented him and the physicists of the 18th and 19th centuries from recognizing the fictitious character of the foundation of this system. The natural philosophers of those days were, on the contrary, most of them possessed with the idea that the fundamental concepts and postulates of physics were not, in the logical sense, free inventions of the human mind, but could be reduced from experience by abstraction, that is to say, by logical means. A clear recognition of the erroneousness of this notion really only came with the general theory of relativity, which showed that one could take account of a wider range of imperial facts, and that, too, in a more satisfactory and complete manner, on a foundation quite different from the Newtonian. But quite apart from the question of the superiority of one or the other. The fictitious character of fundamental principles is perfectly evident from the fact that we can point to two essentially different principles, both of which correspond with experience to a large extent. This proves at the same time that every attempt at a logical deduction of the basic concepts and postulates of mechanics from elementary experiences are doomed to failure. If, then, it is true that the axiomatic basis of theoretical physics cannot be extracted from experience but must be freely invented, can we ever hope to find the right way? Nay, more of this right way, any existence outside our illusions? Can we hope to be guided safely by experience at all when there exist theories such as classical mechanics, which to a large extent do justice to experience without getting to the root of the matter? I answer without hesitation that there is, in my opinion, a right way, and that we are capable of finding it. Our experience hitherto justifies us in believing that nature is the realization of the simplest conceivable mathematical ideas. I am convinced that we can discover by means of purely mathematical construction the concepts and the laws connecting them with each other, which furnish the key of understanding of natural phenomena. Experience may suggest the appropriate mathematical concepts, but they most certainly cannot be deduced from it. Experience remains, of course, the sole criterion of the physical utility of a mathematical construction. But the relative principle resides in mathematics. In a certain sense, therefore, I hold it true that pure thought can grasp reality as the ancients dreamed. In order to justify this confidence, I am compelled to make use of a mathematical concept. The physical world is represented by a four-dimensional continuum. If I assume a Riemannian metric in it, and I ask what are the simplest laws which such a metric can satisfy, I arrive at the relativistic theory of gravitation in empty space. If in that space I assume vector field or an anti-symmetrical tensor field which can be derived from it, and ask what are the simplest laws which such a field can satisfy, I arrive at Maxwell's equations for empty space. At this point, we still lack a theory for those parts of space in which the electrical charge density does not disappear. De Broglie conjectured the existence of a wave field which served to explain certain quantum properties of matter. Dirac found in the spinors field magnitudes of a new sort whose simplest equations enable one the largest extent to deduce the properties of the electron. Subsequently, I discovered, in conjunction with my colleague Dr. Walter Mayer, that these spinors form a special case of a new sort of field, mathematically connected with the four-dimensional system, which we called semivectors. The simplest equations, which both semivectors can satisfy, furnish a key to the understanding of the existence of two sorts of elementary particles of different ponderable mass and equal but opposite electrical charges. These semivectors are, after further ordinary vectors, the simplest mathematical fields that are possible in a metrical continuum of four dimensions, and it looks as if they described, in a natural way, certain essential properties of electrical particles. The important point for us to observe is that all these constructions and the laws connecting them can be arrived at by the principle looking for the mathematically simplest concept and the link between them. In the limited number of the mathematically existent simple field types and the simple equations possible between them lies the theorist's hope of grasping the real in all its depth. Meanwhile, the great stumbling block in the field theory of this kind lies in the conception of the atomic structure of matter and energy. For the theory of fundamentally non-atomic insofar as it operates exclusively with continuous functions of space is contrast to classical mechanics, whose most important element, the material point in itself, does justice to the atomic structure of matter. The modern quantum theory, in the form associated with the names of Broglie, Schrödinger, and Dirac, which operates with continuous functions, has overcome those difficulties by a bold piece of interpretation, which has first given a clear form by Max Born. According to this, the spatial functions which appear in the equations make no claim to be mathematical model of the atomic structure. The functions are only supposed to determine the mathematical probabilities to find such structures, if measurements are taken, at a particular spot or in a certain state of motion. This notion is logically unobjectable and has important successes to its credit. Unfortunately, however, it compels one to use a continuum of the number of whose dimensions is not ascribed to space by physics hitherto 4, but rises indefinitely with the number of the particles constituting the system under consideration. I cannot but confess that I attach only a transitory importance to this interpretation. I still believe in the possibility of a model of reality, that is to say, of a theory which represents things themselves, and not merely the probability of their occurrence. On the other hand, it seems to me certain that we must give up the idea of a complete localization of the particles in a theoretical model. This seems to me to be the permanent upshot of Heisenberg's principle of uncertainty. but an atomic theory of the true sense of the word, not merely on the basis of an interpretation, without localization of particles in a mathematical model, is perfectly thinkable. For instance, to account for the atomic character of electricity, the field equations need only lead to the following conclusions. A region of three-dimensional space at whose boundary electrical density vanishes everywhere always contains a total electrical charge whose size is represented by a whole number. In a continuum theory, atomic characteristics would be satisfactorily expressed by integral laws without localization of the entities which constitute the atomic structure. Not until the atomic structure has been successfully represented in such a manner would I consider the quantum riddle solved. So yeah, Einstein equating kind of talking about how he sees theoretical physics working and how it connects different fields and theories. And a lot of it has to be thought experiments because it's hard to do physical experiments with it. The theory of relativity was a thought experiment, I believe. A number of Einstein's experiments were thought experiments. But yeah, even in the cold, fact-based calculations of science, there needs to be some imagination. But yeah, that'll be it for this episode. As always, educate thyself, think, read, study, learn. Someone tries to tell you something you have trouble believing, ask them to cite their sources. I'll see you all in the next video. Until then, later.